try not to get in the way of your learning by standing in front of the video camera today or coming in for a super close up. But I want to do a short tutorial on vectors so that those that missed due to B2PA and those people who are still a little confused on vectors get a little extra help. So the first thing you need to know about vectors are graphically, a vector just looks like a line segment because that's all a vector is. It's a directed line segment. It's got two parts to it. It's got magnitude, direction, and it can be written in two components, kind of like an ordered pair, an over and up. So if we've got a magnitude, or excuse me, if we have a vector that starts at -1, and ends at 2, 4, the over and up distance to get from start to end on that vector is its components. So we are going 1, 2, 3 to the right, and 1, 2, 3, 4, 5 up to get from start to end. So the components of that vector are 3, 5. Now its magnitude can be found one of two ways. You can plug it into a formula, which I hate, or you can use the Pythagorean theorem, which we all know. 3 squared plus 5 squared equals c squared. That is 9 plus 25, or 34, equals c squared. So the magnitude of that vector is the square root of 34. Now its direction, it looks or appears to be going north and east. So if we want to write that as an angle, we're going to put theta at the starting value and compute theta. Now we all know from last chapter that the tan inverse will give me the angle, and opposite over adjacent is inverse tan of 5/3. Now we just calculate that, and that will give us our angle theta. So, whoops. Sorry, my mode is wrong. I need to be in degrees. So inverse tan of 5/3 is 59 degrees. Now that is coming from the horizontal towards the vertical, which is from the west, or excuse me, the east towards the north, which doesn't make sense. East-north. So we're going to do a complement instead, 90 minus the 59 to get the northeast. So it's 31 degrees northeast. That is just, in a nutshell, vectors. Now we have our formula for finding an angle between vectors. You need to know how to use that. The dot product formula, you need to know how to use that. The unit vector formula, you need to know how to use that. And then adding two vectors together. So for instance, this was one of the problems we had in the homework, number 49, a vector with a magnitude of 8 that's in the same direction as -2, 0. So basically all I did was find the angle associated with the vector -2, 0. Well, from the 0 point on the trig circle, that's 180 degrees. So I did the magnitude times the cosine of 180, comma, the sine of 180. So here's another important formula you should have in your green sheet. Magnitude times cosine theta, sine theta, will give you the components of a vector. Okay, we'll give you the components of a vector. Magnitude times the cosine theta. So this is 180 degrees, so I took 8 times the cosine of 180, sine of 180. That gives me -8, 0, which is the correct answer. This has a magnitude of 8 in the same direction as -2, 0. I also used 0 because if you were to draw a triangle here, the angle associated with that triangle would be 0. Plug it into the formula, but then this comes out to be 8, not -8. But if you look at a picture, that doesn't make sense. To go in the same direction as -2, 0, it can't be 8, 0. It's got to be -8, 0. This next problem is just a dot product. So an example of a dot product, we're taking 3 times the vector w, which, by the way, the vector w is 1, -4. So 3 times that vector is 3, -12. Still got components. We're going to take it times the vector v, -3, 4, multiply those. Now when we do a dot product, That is taking the first components, the x components, multiplying them by another, and then adding the y components product. So -9 plus -48. Notice this is a constant, just a number. The dot product is just a number. Now, what does it mean in vector language? Really nothing. It's just used in several different formulas, which is why we learned it. Now, we're going to take that constant times the vector -2, 2. So what this -57 is doing is changing the magnitude of -2, 2, and also the negative here, 2, 2. Changing this negative is changing its direction. So 57 times 2 is 114, negative, and then -57 times 2 is also -114. So over here, I've depicted what -2, 2 looks like when multiplied by a factor of -57. It reflects it and makes it 57 times as long. Okay. So that's some basics of vectors. Now, the main complaint that those gone had was the application problems. Sorry about getting close to the camera again there. And the application problems, there's several different ones. Before I do this one, I'm going to do a problem that's more like what you'll see on a test or quiz. Just checking the time here. And the main vector application you're going to see is the ramp problem. Okay? If this is a 20-degree ramp and I have a car sitting on that 20-degree ramp, and that car has a weight of, let's say, 400, it's like a smart car or something, 400 pounds. Now, the weight's pulling the car directly down. Now, the components of this, not all of it is going straight down because we're on this ramp. We are on an angled hill. So we want to draw in the components. The angled hill component is this piece, and then the force downward is working at a 90-degree angle to the ramp. So the triangle that we have is 400 pounds on the hypotenuse, and we want to find the x and y components of its force. How much is holding the car up on the ramp, and how much is pulling it perpendicular to the ramp? So triangle congruence tells us that if I drew this straight down, we basically have a right triangle here. Now, we also have a right triangle that I've drawn in. This angle up in the corner is the same for this right triangle as it is for the tiny right triangle. So that implies that this 20-degree angle has to be the same as that 20-degree angle. So now to get our force vectors, we just do some simple right triangle trigonometry. The sine of 20 is equal to opposite x over 400, and the cosine of my 20 degrees is equal to adjacent over hypotenuse. Do the math on there, and you'll get the force holding the car. And I'm not going to do the math because we're running out of time. And here, the y coordinate is going to be the force perpendicular to the ramp. And you can see that in the drawing very clearly. Y is the force perpendicular to the ramp. X is the force holding the car. Because in physics, the force holding the car has to directly counteract the force that the car's trying to roll down the hill with. So if we're holding this thing steady, then this force holding the car up here has to counteract the force of the car coming down the ramp. So that's why we had to use the angle in there, because it's on a ramp. It's not on a horizon. Okay, if it were, it'd be just 400 pounds. That's a weight in a car, but it's on a ramp. So not all that force is acting straight down. Some of it is acting to hold the car on the ramp. Now this is the tough type of problem. This is number 85, and we have two pulleys or two wires that are holding a 5,000-pound weight steady. So this 5,000-pound weight really has two forces acting on it. It's got a horizontal force and it's got a vertical force pulling it down. The horizontal force is actually holding it at rest. So that's why when I wrote my equation for horizontal force, basically I had to set those two pieces equal to each other, because the force from the right and the force from the left, which are these vectors, x1 and x2 here, those two have to be equal to one another. Does But now we got to find x1 and x2. And we can just use a right triangle for that. Now the first computation is actually finding this angle so that I can use, or so that I can find x2. Okay, so this is 24, this is 20, so the inverse tan of 24 over 20 gives me that angle right in there, 50.19. So then the cosine of 50.19 is 20 to my tension vector. And I'm actually, the goal of this is to find what this tension vector, how much magnitude this vector has, if it's acting at an angle of 50.19 degrees. Okay, so in simplest form, I just took my component form of a vector, and to find T2, I took the cosine of 50.19 to get the x2. This is my x2, and then this is my y2. So I took the sine of 50.19. And then I took, for tension vector number 1, tension vector number 1, I took the cosine of 67.38, cosine for x1, and sine for x2, y2. Okay, so x1 and y1. This is triangle 1, this is triangle 2. Okay, so now once I have these vectors, I can multiply them out. T2 times 0.6402 and T2 times 0.7682. Okay, just distribute that out, distribute this out, and then like I said earlier, the tensions this direction have to be steady. They have to hold that weight with no movement. So this vector and this vector are acting with the same magnitude. So basically I just set those equal to each other. Tension 2 vectors equal the tension 1 vector horizontally. Now the weight's pulling downwards at 5,000 pounds. So for my second equation, this one's a little more complicated. I have to take this component, 0.7682 T2, and add it to my horizontal component, vertical component for the second tension wire. So that is plus 923 T1. Those have to add up to be 5,000 pounds. Now note, I have two different variables here. That's easy to fix. Let's solve this equation, this equal equation, for one of the variables. We solve for T2 here. Solve for T2, and then plug this in for T2. And then I'll give you a minute to look at the math. So that's 0.923 T1 plus 0.601 T1. Plug that in here for T2 times my 0.762 or 0.7682 here. So then I just times those two to get this 0.462 T1. Don't forget your T1 when you plug in for T2 in this equation. All right, add them up. Add those two up. Divide. T1's vector is 3,623.2 pounds. Plug that back into this equation, which then indicates the T2 vector is 2,177.54 pounds. And there's that problem. So that was 13 minutes. I may do a second video on the airplane problems before you take your test. I don't have time to do that right now. Okay, but I'm going to try to get this posted on the V drive for anyone who missed class and would like a little extra practice on vectors. Anyway, I hope this helped. And if you have any questions, you can check the Kia page. There is more notes on the Kia page. However, none of it is explained. So good luck. Let me know if you have any questions.